Welcome to a video on graphs of polynomial functions. Before you begin graphing any polynomial equations, it's good to have a graphing checklist, such as the one provided here. This is also embedded in our section 3.4 guided notes. For problem number 1, given the function c of t, find the following 5 parts. The roots of the equation, or c of t is equal to 0, and for each root, determine the number of multiplicity. For letter C, find the t and c intercepts, and then letter D, determine the maximum number of turning points on the graph of the function, and then finally, graph the function. So to find the roots of the equation, that's the same as finding the zeros of the function. Let's go ahead and set that up. The roots of the equation c of t is 0 implies that we're solving this equation for t. T to the 5th minus 6t to the 3rd plus 9t is equal to 0. To solve this statement for t, we'll start out with factoring out the greatest common factor, which is t. We're left with t to the 4th minus 6t squared plus the number 9. Now notice that the second factor of the equation takes on a quadratic form. So this is equivalent to solving the equation u squared minus 6u plus 9 if we let u be defined as t squared. If u is equal to t squared, then u squared is t to the 4th. And therefore, solving the 4th degree equation there is equivalent to solving a quadratic equation. From here, we can apply the zero product property to solve for t, setting each factor to 0. So t equals 0 obviously is one of the solutions. For this one here, as I've mentioned, is equivalent to solving this u equation. We can use the factoring method. We want the factors of 9 that sum to -6. So that would be -3 and -3. The product of -3 is 9, and the sum of these two numbers here is -6. And now to get t to the 4th, that's t squared times t squared. So from here, we have another product that is set to 0. Hence, we can take each of these factors and set them equal to 0 using the zero product property again. So we get t squared equals 3. I'm going to go ahead and just add 3 to both sides and then use the square root property. So remember, using the square root property, we need to remember the plus and the minus sign. So here we have two solutions for t. This statement is identical to the previous one. And so we're going to end up with the same two solutions. T is equal to plus or minus root 3 as well. Now we have altogether 5 solutions, 2 of which are not unique. They have multiplicity of 2. So for letter B of the problem, for each root, determine the number of multiplicity. So for the root of t equals 0, this one has a multiplicity. I'm just going to abbreviate MULT for multiplicity of 1. For t equals the positive square root of 3, since we have 2 occurrence here, this one has a multiplicity of 2. And likewise, for the third root, negative root 3, that is, this one also has a multiplicity of 2. All right, so now moving on to letter C, find the t-intercepts and the c-intercept of the graph of the function. So for letter C, t-intercepts, this implies that the function value is 0. So solving for this equation is equivalent to solving the statement from letter A. So the t-intercepts using those solutions from part A are 0, 0, root 3 followed by 0, and negative root 3 followed by 0. And then for the c-intercept, this implies that t is equal to 0. This is when the input is 0. So setting t to 0 using the c of t function, we're going to end up with basically 0, since all the terms here on the c of t function consist of a t. So once t becomes 0, 0 to the 5th minus 6 times the cube of 0 plus 9 times 0. Adding those together, they become 0. So the c-intercept is the origin. And for letter D, determine the maximum number of turning points on the graph of the function. We call that the maximum number of turning points is defined as the degree minus 1. So if we subtract 1 from n, the degree of this function is 5, and therefore n minus 1 is equal to the value 4. And finally, for letter E, graph the function. So let's go ahead and use part C to graph all the intercepts. 0, 0. Root 3 is approximately 1.7. So 1.7 followed by 0. And then negative root 3, negative 1.7 roughly, followed by 0. And then our c-intercept is also the origin. So this axis represents t. This one here represents c of t. So we have 3 points on the graph. And with the first root, t equals 0, it has a multiplicity of 1, which means that at the point 0, 0, the graph is going to pass through that point due to its odd multiplicity. And then for the other two roots, square root of 3 and negative square root of 3, the graph is going to touch those intercepts because of their even multiplicity. So T for touches or tangent to, the letter P here represents passes through. Now we're going to use the leading term to determine the end behavior of the graph. The degree here is 5, which means they point in opposite directions. Leading coefficient is positive 1, so that means the left end falls and the right end rises. So based on that behavior and where the first root is located, it's going to fall to the left. And then I'm going to read the graph from left to right. So I'm going to go up to the value negative square root of 3 followed by 0, that point there, touches that or is tangent to that, it's going to drop back down. And then in order to pass through the second t-intercept, it has to come back up, passes through that, and then it has to fall back down to go through the third t-intercept, touches that point, then it has to go back up. And again, the right end of the graph needs to be pointing upward due to, again, the leading term test. So here we have 1 turning point, 2 turning point, and 3 and 4. So as long as the graph has no more than 4 turning points, then we are good. So everything matches up. Therefore, this is suffice for graphing the function c of t.